So, hi everybody. My name is Thomas Gibaud, and I work at the École Normale Supérieure de Lyon in France. I'm going to talk about stimuli responsive gel, effect of high power ultrasound on the structure and the mechanics of colloidal gel. And the question I want to address is the following: is it possible to disrupt, break a soft solid without touching it? So, of course, I'm not the first one to try that. George Lucas has done it in Star Wars using lasers, basically. I'm not going to do that. Soccer player do that a lot. Without being touched, they somehow fall down. You can see it clearly with this guy, especially here. His look where he tried to trick the referee, but apparently it didn't work. What I really would like to do is use sound to break solid material. One of the examples is in this Tintin, where Castafiore is a singer, can do it and break wine glasses. So here you see a glass of wine subject to high power ultrasound. And if you fine-tune the frequency of the ultrasound to the resonant frequency of the glass, you can break it into pieces. So that's something I'd like to do, and I'd like to do that with ultrasound. So what are ultrasound? Ultrasound are a mechanical waves that propagate in a media at high frequency, so beyond the audible, so around 20 kilohertz. You can easily produce ultrasound with a piezoelectric transducer, which translate voltage into material vibration here. So this is used in the medical domain for imaging, for example, with echography, but also to break up a tumor, like here with this little mouse. It has been used in granular material, where ultrasound here is focalized and fluidized locally a jam granular material. So the question is now, how do we apply that to soft matter, more precisely to gel? So the ultrasound we're using in numbers, this is what it gives: frequency 20 kilohertz to 500 kilohertz, wavelength 3 to 60 centimeter, maximum acoustic vibration 0.4 micron, pressure 110 kilopascal, and power 1 watt per centimeter square. When we apply ultrasound, it's quite instantaneous. You see that within one millisecond, less than a millisecond, you can reach a stationary regime. And when you turn it off, it's also very rapid. So applying ultrasound, okay. And now measuring the properties of the gel. So we do that with rheology and X-ray scattering. So the idea now is to couple ultrasound with those two techniques. So rheology is done with a rheometer, and that's the rotor you see attached to the rheometer. And instead, we remove the stator and put a piezoelectric transducer instead. And here you have the gap where you put your sample. You see that the gap is 1 centimeter. It's much below the wavelengths of the ultrasound, so there is no resonance in our system. So yeah, we apply ultrasound with the rotor. We measure the rheology properties of our sample. X-ray, how do we do that? Here is a piezoelectric transducer. Then it's coupled to a blade, and the blade is dipped into the gel, and it's a blade that vibrates and transmits the ultrasound to the gel. And then we shine X-ray through the sample just below the blade, and we record the scattered intensity here. The sample we used are composed of carbon black particles. So carbon black particles are obtained through the combustion of mineral oil, and depending on the combustion condition, you can form different types of particle. What's important to know is that it's composed of primary particle of about 10 nanometer, which has fused together to form those carbon black particles. and you can have many different carbon black particles, spheroid, linear, and fractal. We characterize those carbon black particle with X-ray scattering. So that's how it plays. You shine X-rays through your sample, and far away you record the scattered intensity as a function of the wave vector Q. So the wave vector Q, the scattering wave vector Q, is the x-axis of your plot, and it's basically a measurement of the length scale you can probe with X-ray. And the intensity you measured is proportional to the Fourier transform square of the electron density of your sample. So that's the resulting spectrum you get for our carbon black particles. So the carbon black particles we use are Vulcan XE72R, and here this is the form factor of the particle. That is to say, the scattering obtained from a very, very dilute suspension of carbon black in mineral oil. And so the scattering is only a function of the shape of the particle. There is two regimes that we can see. At high Q, so small wavelengths, you measure the fractal dimension of your particle. Here it's 2.2. And at low Q, long wavelengths, you measure the radius of gyration of your particle. And here it's 60 nanometers. To fit the data, we needed a polydispersity of about 20%. Now, you take those particles, you put them in mineral oil, and you increase the concentration, and that's the kind of viscoelastic response that you get in the linear regime. So it's G prime elastic modulus, G double prime loss modulus, a function of the oscillatory frequency. There is two parts in this master curve. At low frequency, you measure the elastic plateau, that's the elasticity of the gel network. And at high frequency, you see that G double prime dominates, and that's a dissipation mechanism. And it's related to the viscosity of your background. You can characterize this elastic plateau by doing a strain sweep experiment. That is to say, you measure G prime and G double prime, and you logarithmically increase the amplitude of the strain. First, you have a linear regime up to roughly gamma nonlinear, which is about 1%. Then you have a steep decrease of the elasticity. Eventually, they cross over here, and that's the yield strain. Beyond this yield strain, the gel is flowing. There is very little aging in carbon black dispersion. Now, let's see the effect of high power ultrasound on the gel, on three different gels, actually, calcite, silica, and carbon black gels. So, no ultrasound, G prime is constant. You turn on the ultrasound, G prime decreases. You turn off the ultrasound, you have a partial recovery of the initial elasticity of the gel. What we're interested in is the softening effect due to ultrasound. So it's delta G prime divided by G0, where G0 is the initial elasticity of the gel. You see that for the three different gels, there is the same effect. As you increase the power of the ultrasound, the softening effect increases. But it's all over the place. But we found an empirical number, gamma, that allows us to rationalize this curve and to make a master curve of all this data. And this gamma number is a ratio between the strain induced by the ultrasound divided by the nonlinear strain of the gel. So let me get that a bit more clear. So in this plate-plate geometry, when you oscillate the bottom plate, you create a squeeze flow. And it's well known that the squeeze flow produces a strain which is equal to R, the radius of the geometry, times the amplitude of the ultrasound divided by 2h squared, where h is a gap. And this value is about 1% at max. The only value which is about 1% in the gel property is a nonlinear strain. And that's how empirically we build up this dimensionless number. So there is clearly here room for modeling and understanding why this could be the right number. But empirically, this works quite well, as you can see with this, all those curves that collapse on the master curve when plot as a function of gamma rather than the ultrasound pressure. Let's see a little bit more in detail what's going on with ultrasound. So here you have the viscoelastic spectrum as a function of F when there is no ultrasound and when ultrasound are turned on. When ultrasound are turned on, you see that G double prime, there is a minimum that appears in G double prime. And this minimum is also seen in glass sample, where you see here G prime and G double prime as a function of frequency, and there is a minimum in G double prime, which result from two mechanisms: the beta relaxation at high frequency, which is a jiggling of the colloid within its cage due to thermal motion, basically, and the alpha relaxation, which is the escape of the colloid from its cage formed by its own neighbor. And this requires a collective rearrangement of the surrounding colloid. So the question now, what is, for our gel under ultrasound, the alpha relaxation mechanism? Is it cage hopping or is it something else? It's probably something else, and because it's not a glass, it's a gel. So to do that, we want to probe the structure of the gel at the particle level. And that's what we do with scattering. So here is the scattering intensity as a function of the wave number for 3 different conditions. Red before ultrasound is turned on, red before ultrasound is turned on, green after ultrasound is turned off, and blue when ultrasound is turned on. So what you see is that at the particle level, so at high Q, small wavelengths, nothing happens. The ultrasound does not affect the carbon black particle. It only affects the small wave number, so the long wavelengths, and that is to say the gel structure. And the gel structure is characterized by the power law exponent minus P. When P is between 1 and 3, which is the case for the gel with no ultrasound, what you measure is exactly the fractal dimension of the gel, P. So you see when there is no ultrasound, fractal dimension of the gel is 2.6, and when you turn it off, after a while, it's about either 2.6 or a little bit below 2.2. However, when the ultrasound is turned on, you see that the exponent P is much larger than 3, means that it's a different scattering method. What scatters the intensity here is interfaces. So you create interfaces that increase the scattering of the gel or dominate the scattering of the gel, and that's due to interfaces. And those interfaces, we interpret them as microcrack produced by the ultrasound. So it's the interface between the background solvent and the gel. Here is a picture of it. So those are the microcrack. You see that the scattering intensity is intermittent, so it's a dynamical effect. You programmably open microcracks, close them, open them, close them, etc. So those microcracks would explain the softening of the gel and would also explain the alpha relaxation. So you have global rearrangement of the structure through the formation of microcracks. Just to I'm going to skip that. Basically, ultrasound also affects the gel flow, and it facilitates the gel flow. So to conclude, I've shown you a new class of material, which are Rheo-acoustic gel. The interaction criteria for gel to be Rheo-acoustic is gamma US divided by gamma nonlinear equals to 1. And I've shown you that higher power ultrasound can weaken the gel due to the formation of microcrack. It also eases the flow. So what's next? The next is to optimize the formulation of Rheo-acoustic material and study the shear thickening transition with high power ultrasound. Many thanks to my co-worker, especially Noémie Dagès, who did her PhD on the subject. Thank you for your attention.